This short presentation is going to be about gravitational lensing. What gravitational lensing basically is an amazing optical effect which occurs in space. Scientists can use it to look at distant stars and galaxies which were formed in the early days of the universe. It's like having a cosmic magnifying glass. To understand about gravitational lensing, we need to first know about 5 things: light, lenses, space, gravity, and relativity. Let's begin with light. We all know light travels in straight lines. That's why, for example, when I shine this torch in my hand, it casts a shadow. This is because the light can't go round my hand, meaning that the area behind is dark. But is this completely true? The answer is, in fact, no. Light can change direction when it passes from one medium into another medium. An example of this is this pencil. When I look at it in air, it is completely straight. When I put half of it in a glass of water, the half in the glass of water seems to be bent and magnified. That's because the light travels from the air into the water, which is a different medium. And when it goes into the water, it gets redirected, meaning that the pencil seems to be bent. This process is called refraction. Refraction is very complicated, but basically all you've got to remember is that it happens when light travels from one medium into another medium, and the light changes direction. But also remember, refraction is used very cleverly in lenses. What are lenses? A lens is a curved piece of transparent material such as plastic or glass, which uses the effect of refraction to redirect the light that travels through it. The way a lens works is that the light beams travelling on one side are parallel, and then when they go out the other side, they are redirected so that they converge on one point, the focal point. In this case, the focal point is my eye. This lens, magnifying glass, makes images bigger. There are many different types of lenses which can make images sharper or bigger. For instance, microscopes, glasses, binoculars, telescopes, and magnifying glasses. We've looked at light and lenses, but how does any of this relate to space and astronomy? This is where relativity comes in. One of the most well-known parts of Einstein's theory of relativity is the equation E equals mc squared. And the crucial part in this is the equals. It shows that the E and the m and the c are all related. E being energy, m being mass, and c being the speed of light. So they are all connected. Here's an example. Einstein says that you cannot go faster than the speed of light. Well, you might say, why couldn't it just have more powerful engines? Well, the truth is, the faster you go, the more mass you have. And because mass and space are connected, the more mass you have, the more you warp space. It is a bit weird, but if you keep on going until you reach the speed of light, your mass will be so great that it will have warped the space around you too much for you to actually travel in it anymore. The only reason why light can travel at the speed of light is because it has no mass. If we want to know about gravitational lensing, we will also need to know about gravity. Gravity was discovered by a man called Sir Isaac Newton. He explained it as the force which makes objects with mass attract each other. But ever since Einstein's theory of relativity, we have thought of it in a slightly different way. We have thought of it as the effect where mass warps space. Here's an example. Imagine that this bed is space, and this marble is a very dense star. Let's see what happens when we put it in space. It has bent the space around it. This is the star's gravitational field. Now, imagine that this smaller marble is a less dense object, probably a meteor. Let's see what happens when we put it in the gravitational field of the star. It gets attracted to the star. This is the force of gravity. But only really huge, dense objects bend space enough for us to notice, and they don't come much more huge than galaxies. This brings us to gravitational lensing. Gravitational lensing acts in a similar way to a lens, in that it redirects the light. Simply, if a curved piece of glass can act as a lens, then why not a curved piece of space? For gravitational lensing to work, all you need is a distant light-emitting object and an observer, us, and an object in between massive enough to warp the space around it. We could say that the distant object could be, say, a star, and the object in between could be a galaxy. Suppose the light rays from the distant light-emitting object happen to travel through the curved, bent space made by the galaxy. They will be redirected to another point, just like the focal point in a lens. Here, hopefully this explanation will help you understand it. Imagine that this marble is a distant star emitting light, and this marble is the galaxy with the bent curved space around it. And imagine that this marble is the Earth, where we are looking at the star through our telescopes. Now I'm going to try and show you the path of the light using these pens. So first, the light travels in a straight line until it hits the curved space. Then it is redirected so that it then is travelling towards the Earth, where we observe the light. But we think that the light has always travelled in a straight line. Therefore, we think that the object is actually here, because we observe these light rays, and that's where it would be if it always travelled in a straight line. So we actually think the object's here, but it's here. The first effective gravitational lensing ever observed was in 1979, where we saw a double quasar, Q0957-561, which was actually only one quasar, but because of the effect of gravitational lensing, we saw two images in the sky. This is because, in this case, the lens, a large elliptical galaxy, was not a very good one. Like when you look through glasses and they're out of focus, you start seeing double. The image was almost in focus, but it was just out of focus enough for us to see two images in the sky. So the lens, in this case, wasn't very good, but it started the whole thought of bent space acting as a lens. Amazingly, Einstein even predicted this, but didn't feel the need to publish his work, because he thought the effect would never be observed. Also, gravitational lensing can help us find things as small as planets. Imagine that we were looking at a distant light-emitting object using a star as a lens. If the star had planets going around it, the shape and strength of its gravitational field would change periodically as the planets go round, which would also change the image of the distant light-emitting object. So if we see the image of the distant light-emitting object change ever so slightly periodically, we can work out whether there are planets orbiting the star. Clever. Abell 1689 is one of the most massive galaxy clusters known to man. With its trillion stars plus dark matter, it acts as a 2 million light-year wide lens in space, magnifying and sharpening the galaxies behind it by up to 10 times. It has enabled us to see some of the most distant and earliest galaxies ever. Strong gravitational lensing. Like the double quasar Q0957-561, strong gravitational lensing is where the lens has so much mass it creates multiple images in the sky. More recently, we've seen galaxies acting as extremely strong gravitational lenses. But we've worked out the only way that they could be that strong is that if they had a huge dark matter concentration. Maybe in the future gravitational lensing could help us find out a bit more about dark matter. Overall, I think gravitational lensing is a very interesting and important topic. It can help scientists discover more about the distant stars and galaxies and to calculate their positions even more precisely. It is also very important in astronomy because not only can it help astronomers find out whether there are planets orbiting distant stars, it may also be able to tell us a bit more about one of the great mysteries of astronomy, dark matter.